I'm going to record this tonight because we have quite a few people missing, so try not to say anything that you don't want forever living in YouTube and social media world and that kind of stuff. So, cool. So just to refresh on where we are, so we're in the third of 5 sessions. And this one is focused on, and again, go back, basically the 3 things are, where are we, how do we want to get there, how do we want to arrive? So we want to arrive safely and quickly, so this is all about fixed and movable objects, weather, managing air, and then starting to get a little bit into some of the tactical navigation stuff that's important for racing, and we'll go there even more deeply in the last session. No worries. Just I am recording this, so that way, don't say anything you don't want to capture. So, how do we want to arrive? What do I hear playing?
What do you know? What?
Do I hear something playing?
It's
a radio.
radio.
Yeah. So we want to get there safely by avoiding hazards and with minimal navigation error, and we want to get there quickly. So we want to get there through an optimal course, and once we pick that optimal course, have close to optimal execution. It's really, I'm going to turn these lights off because we're going to have a video. It's a bit more challenging to record. See if you can see this. You guys see that? So if you don't know what that is, that was the grounding of Vestas win in the last Volvo Ocean race. So here we have the best offshore sailors in the world, one of the best navigators in the world, and they run aground in the middle of the ocean. So, I mean, how does that happen? There's been a lot of research done into what actually did happen here, while not completely conclusive, certainly there was some challenges related to the way the navigation system they were using was set up. If you use GPS, different levels of zoom will have different levels of information available on it. But, my point of showing this is that this can happen to the best people in the world, it can happen to us, right? So it takes vigilance to make sure that we really understand where we're going, and so we know how we get there safely. So, one second. Okay, got it. So, this is, by the way, this is what they hit. So this is Madagascar, this is Africa. They were going along this ridge here, and they even talked about the fact that there was some shoal water before the race, and even though they talked about it and they knew about it, they still ran around because they were too close to it. So when you think about things that you can hit or hazards, right? There are 3 main categories, right? So there's rocks, shoals, coastlines, land, basically, right? By the way, so I brought the sailors back, the Rye Rumble sailors back today from American. After I got docked, I was down on the boat cleaning up the boat, and I watched somebody come 30 yards inside of that red that marks the rock. I call it Turkey Rock, that's off of the A dock. They had an outboard. It was like a 30-foot boat, but it had an outboard. I was shocked they didn't hit it because it was still mid-tide. There's a lot of rocks on this side, especially on this side of the Sound, right? Long Island Sound. Who knows what created Long Island Sound? Glaciers, exactly, right? And so, as Long Island got pushed away from the Connecticut shore, all the rocks stayed here and the sandy shore ended up over there. So I guess if you're going to run aground in Long Island Sound, it's better to run around on the Long Island shore than it is the Connecticut shore because it's rocky. The second set of hazards that we have to manage for are other boats. right? So we have to know the rules of the road, we have to know what other boats are probably going to do, we have to know what we're going to do, we have to know how to communicate and signal those things. And then the other thing that's changing all the time is the weather. So the other category of stuff that I would say really can cause some real challenges in navigation and in either sailing or powerboating is the weather. So those are the things that we're going to talk about today, right? Is we're going to talk about how to identify and how to manage each one of those. And we're going to start with 3 short videos. So let's see if this works.
Extraordinary background there for the extreme sailing series at the top market, black blue for Austria in the second. As we look through a sea of sails and remember the hostile.
Oops. Who has right of way? Oh, sorry.
What is?
Who has right of way? I don't want it to play again. Stop. Who has right of way? Sailboat or powerboat?
Oh.
It's a push. Yeah, but those things take like miles to stop. So
Actually, I don't know.
I have no idea.
It's a really good question.
But I feel like a boat that big.
So how many people think that in this situation, how many people think the sailboat had right of way? Okay. How many people think the powerboat, that big yacht had right of way?
Yeah, the powerboat can't stop. I think it takes like so long to stop.
It's a vessel restricted in maneuverability. Okay? So one of the things that we will talk about, which has right of way over a sailboat. So one of the things we'll talk about, and everybody should have on board, if in the boats that you're on, you have to by law have this on the boat. It's referred to as the coal regs because it used to be called the prevention of collisions at sea, the regulations for prevention of collisions at sea. It's now technically called the navigational rules. That's what technically they changed the name of it. But this basically describes in all these situations, and we'll go through some of this, who has right of way in different situations. And so there's a hierarchy of who has right of way, starting with an emergency vessel, right? Then going to a vessel not under command. Then going to a vessel that's restricted in maneuverability. Actually, there's one in between that, which is if it's a vessel that is restricted in maneuverability because it's doing mining or dredging activity. So it's got lines out, right? So, for example, and I've had this conversation with Nick and other people, Serenity's a good-sized boat. I can't leave the channel off of any dock because there's rocks on either side. I am a vessel that's restricted in my ability to maneuver. If there's a sailboat sailing in the channel and I've left the dock, I technically have right of way. Which most people don't know, right? If there's an oppie out there sailing, I technically have right of way. Now, obviously, I wouldn't exercise that, but this guy can't stop this boat, you know? And he's still close to shore, and so, you know, he's in a defined shipping lane. He doesn't have any choice of where he goes. That's why he sounded his horn 5 times. That's the, oh crap, that's the emergency signal. That's basically the signal that if you're not sure of what someone's doing or you think there's danger, you sound your horn 5 times. So he was sounding his horn 5 times to try to get that guy to get out of the way.
I'm just sure they didn't drive. I mean, I know that's not one of the things. I just
They should have. They should have done something to get out of that guy's way, right?
like I don't know what ocean this is, but like even jumping out of the boat, like they almost just killed themselves. I don't know.
So this is actually cows. The Isle of Wight, which is in just off the coast of England, this is looking north off the Isle of Wight from the yacht club, the Royal Thames Yacht Club. So this is the Thames River, is what this is, the end of the Thames River. And it's a really neat place to sail, actually. I love sailing over there. A lot of current though, and a lot of commercial traffic. Just like there's a lot of commercial traffic in Long Island sailing. And so there's another rule that I call the rule of tonnage, that basically if there's a boat that's bigger than you, you should stay out of this one. Now, if you wanted to talk to this boat, if you wanted to have a conversation with this boat, let me see if I'm still recording or something. Yeah. On the VHF radio, what channel would you call him on? Anybody know?
I don't know. I just made that up.
Isn't it in the 60s?
It's not.
42.
A boat like this is always monitoring 2 channels. Every boat should be monitoring 2 channels. What 2 channels must every boat monitor? 16's one of them, that's not the one the calling on though. 16's one of them. 13 is the other one. 13 is the primary ship-to-ship and ship-to-shore communication channel. If you're calling a bridge, if you're calling another boat, you call them on 13. And we'll talk about radio calls. So that's one of the things we have to obviously avoid. That's the money shot, yeah. I'll say. So we probably want to avoid being in conditions like that, if we at all can. Just so you know, that boat, I researched that boat. That boat is looks like a submarine. That's not a submarine, because that's not the boat. I'm not very good at drawing boats. It's probably like a big bulb underneath it here, and it's got a bunch of big stuff stacked behind it. That boat is like 1,100 feet long, and the bow off the water is 65 feet.
That was 60. That was like a 100-foot wave.
That was probably close to a 100-foot wave.
Crazy.
Because, you know, this superstructure is another like 100 feet off the top. So the height of this boat overall is like 160 feet off the water. And the bridge it's not all the way at the top, but the bridge is, you know, it's got kind of a fly area here, and it's got the windows, which are usually reversed like that. And water splashed on those windows. That was a big wave. We don't want to go there. You know? So we want to make sure that we don't hit land, we want to make sure that we don't hit other boats, and we want to make sure that we don't put ourselves in harm's way with weather. Okay? So we're going to talk about the first of those, which is we want to make sure we don't hit land. And that is why we have in front of you your nautical chart. Because does a nautical chart show boats? No. Does it show weather? No. It shows everything else though. It shows rocks, shorelines, shoals. So this is an actual shot of your map. So if you want to take a look at it in front of you, this is Long Sand Shoal. So find Long Sand Shoal, which is, you know, kind of near the top of the shoreline. And I mean, you can just see that this is covered with things that are dangerous, right? And we want to make sure that we avoid. So we'll talk about some of this in some more detail. But just so you know, the white water is deeper, and the blue water is shallow. See these individual numbers here? Those are the depth. The depth in what? Can anyone tell me? Somebody said feet. Did you say feet? Why do you think it's feet? Different maps show different things. This one is feet, but how do we know it's feet? Angus, how do we know it's feet?
I was going to
Anyone know why it's feet?
Because that's the unit of measurement we use in America.
Look at the bottom of the chart.
Oh, it's in the bottom right.
It says soundings in feet. So soundings in feet. Do you know what most offshore charts are shown in?
Meters.
Nope. Fathoms. How many feet are in a fathom?
6.
Excellent. 6.
Because it has a thing on the bottom.
Jenna. So good. It actually shows you right here that 1 fathom is 6 feet, and then you can also translate to meters. So most English-speaking charts are feet when you get close to shore, and fathoms when you're out in the middle of nowhere. Most European and Asia charts are measured in meters. So Long Sand Shoal is obviously shallower than here. This water's, 159 feet, 80 feet, 75 feet, and Long Sand Shoal 6, 7. There's some 4 and some 3 over here. So, that's why it's got markers on it, right? Obviously, you got the coastline up here, right? What about this? We have a hens and chickens out here. They have the hens and chickens as well. There's a lot of hens and chickens in the United States.
Are these measurements taken at high or low tide?
Excellent question. Look on the chart and see if you can find something that tells you. We will actually talk about this later on today, but since you asked the question, someplace on every chart it tells you. They're all done the same way, by the way, but it tells you. It's in the top. It's actually not far from Long Sand Shoal.
Mean, low, low water. It's right there.
It's in the top right.
Soundings in feet at mean low of lower water. Here, let's just go to this right now. So check this out. Here you go. How many people have been to the Bay of Fundy?
No.
Up in Maine.
Up in where?
Oh,
Yeah, it's
so far out.
like 34 feet, right? The tide difference or something.
It is actually 54 feet.
Yeah.
A 54 foot tidal swing is how much, I mean, so look, I mean, here's people, and that tide comes all the way up to here. It's a 54 foot tidal swing
We're playing again.
every cycle.
There's like this one place in Cape
It looks
Cod
like carrot soup.
where it goes to like,
Tomato soup.
it's like all the way out. It goes out like a mile.
Yeah.
Brewster Park.
Yeah.
But why is that?
So there's a place up in northern Alaska where fishermen die all the time because they die because it's a very, very shallow slope. There's like a 14 or 15 foot tide, and this whole thing is a shallow slope. It's like a mile and a half long. So people will walk and don't know, they'll walk out on it at like a mile and a half or 2 miles, right, to get to actually the point where it goes off fishing. Tide starts to come in, they can't get back to shore fast enough because it's like a 13. So in an hour, it's gone up like 8 feet. You know, it's totally up. So what causes the tides?
The moon.
Partially.
The gravitational force of the moon.
The water is going close to like where the moon is.
Yeah. Is that the only thing that influences the tide? Sun does as well. So about 75% of the tide is influenced by the relative position of the sun, and, of the moon, and about 25% is influenced by the relative position of the tide. That's why the tides are biggest when the moon and the sun are in alignment. So when you have a new moon or a full moon, so a new moon would basically be the moon and the sun kind of on the same side because you're looking only at the dark, if you will, at the moon, or full moon on the earth side. That's when the tides are at the biggest. And this is how they measure tidal range. So these are important terms because there's some questions on these. So if you talk about mean sea level, that's basically the average of where the water is. So if you took all the high tides, all the low tides, the fact that some high tides are higher, some high tides are lower, that is where the mean sea level is measured at, right? Then you have what's called a mean high water and a mean low water. That's MHW and MLW. This is the mean typical tidal range, the average tidal range that you get. So who knows what the tide is here about?
6 feet.
It's about 8 feet. It might actually be, it's either 7.9, 8, or 8.1, I can't remember. Then you have something that I'll explain, it's called the diurnal tidal range, which gives you the mean high of higher water and the mean low of lower water. Okay? And the way these charts are calculated is they've basically taken the tidal cycle over what's called a metonic cycle, which is 235 lunar months, because that's how long it takes for the moon and the sun to be in the exact same position, is 235 months. It's about 19 years. So basically what they've done is they've taken 19 years of tide. Now this stuff is all done in computer models now, confirmed with actual soundings that they go out and take. So in theory, the numbers that you see here are the lowest you should ever see, because they take all of these higher of high waters and lower of low waters, and they average all the low ones. So if you look at a tide cycle, towel. Hold on one second. White towel. Smells a little. Isn't quite damp. This one looks like a good one. This is towel belonging one. Going once, going twice. Okay, it is the cleaning rag. And look, you guys experience this because you're sailors, you've been sailing dinghies, so you'll have a high tide that leads to a low tide that leads to a higher tide and then typically a lower tide, right? So that's kind of the way that's the way the cycle goes, right? So what they do is they take the average of all these highs and the average of all these lows, and that's what's on the chart. Make sense? Excellent question. Glad we jumped in. Okay. So what's the fundamental problem? The fundamental problem is that's kind of what the Earth looks like, and we have to get the Earth onto a flat piece of paper, which is hard to do. So, we mentioned this last time, but this guy named Mercator, Gerardus Mercator, who lived back in the 1500s, basically came up with a concept to take the globe and break it up into individual maps.
Roll it out.
And that's still, say again?
Oh, never mind.
Yeah, and so what it does is it creates distortions, but in any one map, the distortions are so small, it fundamentally doesn't matter. Basically what it is, it's a cylindrical map projection. So this is what a Mercator is. So you can see how it exaggerates things down here and up near the poles. So Antarctica is not really this big, but because you took the globe and you stretched parts of it to make it cylindrical to match the equator, that's what it looks like. There are other ones, and you've probably seen these kinds of images before, and you don't need to know these names, you just need to know the Mercator one, because it will ask you on the test, one of the multiple choice questions is, what type of projection is a map? And it says, by the way, on every map, sorry, I didn't mean to hit that page up button like that. Someplace it says on here that this is a Mercator projection, and it says it, I just found it, that it's very close to the soundings in feet at mean low or low of water. So if you look right above that, you found where it said the soundings in feet, so just right of the NOAA symbol up at the top, it says Mercator projection, scale 1 to 80,000 at latitude 41 degrees 7 minutes, North American datum of 1983, World Geodetic System of 1984. The hell does that mean? So what this means is that this map is a Mercator projection. It is a Mercator projection, which means it takes the little space that we're looking at up here, which is the eastern part of Long Island Sound, and it made it look cylindrical. Basically, it means that the lines that run from the top of the map to the bottom of the map, which are lines of, ones that run from the top to the bottom are longitude.
Let's go.
It makes the longitude lines on the map parallel, because the longitude lines aren't exactly parallel. They're parallel at any given point, but this shows them as parallel at 41 degrees, 41 degrees 10 minutes, 41 degrees 15 minutes, 41 degrees 20 minutes, and they're not really parallel. They're getting closer together as we get up towards the poles. So that's what the Mercator projection part means. The next thing is scale is 1 to 80,000. That means that if in real life something is 80,000, on this chart it's 1. So if something is 80,000 inches, on this chart it would be 1 inch. If something in real life was 80,000 feet, on this chart it would be 1 foot, right? So Long Sand Shoal, for example, I don't know how long that is, but you could scale it. So if you wanted to measure from point 1 to point 2 at the end of Long Sand Shoal, you could do the math and it would be about 1 to 80,000. It says 1 to 80,000 at 41 degrees 7 minutes, which is usually the middle of the map. So it says in the middle of this map, 41 degrees 7 minutes is the middle. And then the last two things, the North American Datum of 1983 and the World Geodetic System of 1984, those are just the formulas that are used to take a non-spherical Earth, because you gotta remember our world is kind of squished, to take a non-spherical Earth and make it appear spherical.
Earth is flat.
Say again? Yeah, it's kind of, it's squished at the poles. Okay? So, if you want to know how to read a chart, you want to know what's on a chart, where would you go? Well, guess what? There is actually a chart number 1. And I'm going to pass this around. Chart number 1 is a book. And I did this for a while. I haven't done it in a while, but I used to walk on people's boats and I say, where's your chart number 1? Almost nobody has this. And everyone should have it. Because the key to read all this stuff on this map isn't anywhere on this map. Some of it is. Some of the common stuff is there. But the majority of it is nowhere on this map. It's all in here, which is chart number 1. So why don't you take that and pass around, flip through, and I'm going to go through kind of a few key elements of it. Okay? So right at the beginning of chart number 1, first or second page, it basically tells you all the things that exist on a map, and it gives you a key over here that tells you, so it's off focus. Now I see something with letters. Is that better? Okay. A little bit better. Right. So number 18 down there. Oh, well, that's not a good one because it stops at 14. It's a 2-page thing. Number 3 is the reference ellipsoid of the chart. That's what we just talked about. So where's number 3 on here? It's on a different place on this chart. But what we were just talking about is the reference ellipsoid. Basically, it's the Mercator projection, what the scale is. Number 10 is the chart type. So it's key to tell you what all this stuff is. Here's Cook Inlet, right? Oh, here it goes. Here's that North American datum and all that stuff. That's right here, this number 3. So it's a key to tell you what else on the chart. It also tells you how to use individual things. Remember we were talking about the compass rose, right? So it explains the compass rose. And it says that cursor pick site for magnetic variation at a point. Cursor pick site for magnetic variation at a point. Got it. At a point, whereas this is along a line. Okay. Again, but it basically tells you how to work through an example of east and west, like we did in the last time. It explains how that works. It goes on to tell, okay, landmarks. Here are landmarks and what they look like on different charts. I should mention back on time. There are different kinds of charts. So this is a NOAA chart. How do we know it's a NOAA chart? Right up at the top is a little NOAA symbol with the eagle on it. And it probably says it 2 or 3 other places. The circle right above the chart name. So that is where the majority of the charts come from. But there's also the National Geospatial Intelligence Agency. You have what's called RNC, which are rastronautical charts, which are basically electronic versions of this. You have electronic ENC, electronic navigation charts. So these are the charts that would be in a chart plotter that look different from this, right? So the problem with why Vestas Wind ran aground is they weren't cross-referencing to a raster or to a NOAA chart. They were relying solely on their electronic navigation chart at the time that they ran aground. And the zoom depth that they were on their GPS, the zoom depth further in and the zoom depth further out, both of them, one in and one out, showed the reef. The one they were on, defect in the software. It doesn't show the reef when they were on, the zoom level of 5 nautical miles. I'm making that up, I don't know what it was, right? So if you ever go and play with something that has electronic navigational charts, that's why I personally never rely on electronic navigational charts. I will use them as a point of reference, but I always want to go here because I know that's the thing that's been officially announced. But NOAA's nice, and what they said is, look, we'll not only tell you what these things mean on our NOAA maps, there's the one that publishes charts one, we'll tell you what they look like on the other maps as well. there's a section in there, what I just explained about tides, there's a section in there that explains all of the details of tides. So you can go into tide levels and charted data in book number 1 and get the explanation